This video is a continuation of the previous video which looked at an overdamped harmonic oscillator. So we're going to look at the second option here, which is going to be a critically damped oscillator. So in this option here, what we're going to do is we're going to look at the possibility of the value b squared minus a squared equaling 0. In that case, our b would have to equal our a. So in that case then, our roots for our equation are going to be m1 is going to equal m2 is going to equal our value minus b equals minus a. Okay, so now the general solution for this type of differential equation, again it comes from the differential equation toolbox, is going to equal x is going to equal c1 e to the minus at plus c2 t e to the minus at. Again, I'll go through that in the snippet section, and whenever I do a snippet section on the solutions for differential equations. So if we were to put in the initial conditions, and again initial conditions are telling us that at t equals 0 we define the equilibrium position as x0, and at that point the mass isn't moving, so the velocity dx by dt is also going to be equal to 0. Okay, so what we're going to do is we're going to put these in to the above, see if we can find solutions for C1 and C2. Okay, so when t equals 0, we're going to have that's t will be 0 there, so that will disappear. That will be e to the 0, which will be 1. So we'll have x0 is going to equal our value of what, C1. Okay, now if we were then to go ahead and differentiate this, so dx by dt, so what we're going to have is our first one here is going to be minus c1 times a e to the minus at, and the second term here, I've just put it down below here. Okay, so the second term here is going to be, well, c2 is a constant here, and it's a product rule for differentiation, so we could differentiate the first one. So we differentiate t, we just get 1 and multiply it by what's left over, so it's going to be e to the minus at, and the second one we can differentiate e to the minus at, so you're going to have minus a e to the minus at, and we're going to multiply it by the value t, so we'll have that value for t there as well. Okay, so you can see there then, if you put the initial conditions in for this particular the derivation here, then you can see that at t equals 0, well, this section here is going to disappear, so that's going to disappear. That's going to be give us a value of 1. Okay, so we're going to have a c2 for that one there, and we're going to have again that will give you a value of 1, so we'll have minus c1a. Okay, so the same that there is going to equal 0, so then you can just say that our value c2 is going to equal will be c2 minus c1a, so we take the minus c1a across, we say c2 equals c1 times a value of a. Now, but we already know that c1 is equal to x0, so we can write that as that's going to be equal to x0 times a. Okay, so if we can put these values back into the general solution above, then what we're going to have is we're going to have our value x is going to equal our c1, which is x0, so it's going to be x0 e to the minus at and we're going to have our value of our C2, which is going to be our x0a, x0a times te to the minus at. Okay, so that then, if we gather like terms, we can say that x is going to equal x0 e to the minus at times 1 minus at. Okay, so that there is a formula for a critically damped harmonic oscillator. Now we'll go and have a wee look at that in our graphical calculator. We can see that actually in motion. So let's see if we can bring this up. Okay, so all we have here is that same equation that we've just derived, and we have x up here, which is just the initial displacement of the spring, and along this axis is the time. Okay, so in that example we've got here is the spring is initially displaced to this height here, so it's just above 1, and whenever the spring is let go, the mass is let go, it just drags the mass back in, okay, and down further and further down to its equilibrium point, which is just at x equals 0 here. Okay, so you can see there that there is no oscillation in that system. So again, we can run this value a, we'll run x0, so x0 just changes the initial displacement. Okay, so that's initial displacement, and the value of a here, okay, it just changes as you can see here. Okay, so it just changes the length of time it takes for the system to move back to the equilibrium point. Okay, so I suppose that value a again is just related to the stiffness of the spring. Okay, so I can press play in both of these, and we can see that at no point does this system oscillate. So you can look at that and say, well, okay, well, what's the difference between that and the overdamped situation? Well, the only things that makes this special is that this sits on the very, very edge of the overdamped situation. Okay, so it means that if there's any small change in the viscosity, or say the mass of the system, or if the spring constants were changed a little bit, then this would have the propensity to go into the next phase, which would be a system which would be underdamped, which would have a potential to oscillate. So this, if you like, is sitting in a sweet spot just before the oscillations potentially could start. Okay, so that's all there is to this video, quite short and sweet. The next video we'll go on and we'll look at what happens in a more interesting example of an underdamped system. Okay, so thank you for listening and goodbye.